Okay, so welcome to week 10's problem solving session. So let's first quickly recap what we did in this week. So in this week, we saw the connection between communication complexity and circuit lower bounds. So let's first quickly recall what the communication complexity is. So for a relation R, which is a subset of X cross Y cross Z, CR, or the communication complexity of R, is the number of bits that Alice and Bob need to send to each other on input X and Y to compute Z, so that X, Y, Z is the relation. So you have Alice, you have Bob. Alice has X, Bob has Y. They send messages to each other, and their goal is to compute Z so that X, Y, Z is in R. So the goal of sending messages to each other is to compute such as Z. Okay, and the communication complexity is just the number of bits they need to communicate to figure out such as Z. Uh, then we saw the Karlshammer-Wigderson theorem. So this theorem gives us a relationship between the communication complexity and the depth of a circuit. Excuse me a minute. Okay. So what this theorem says is that for any Boolean function f from 0, comma 1 to the end to 0, comma 1, the depth of f is equal to the communication complexity of R of f. So here depth of f is the depth of the best depth of the smallest depth circuit computing f. And they show that this is exactly equal to the communication complexity of the relation Rf, where the relation Rf is a subset of f inverse 0 cross f inverse 1 cross n. And it's defined as the set of tuples x, y, I, so that x is in f inverse 0, y is in f inverse 1, and I is in n, such that xi is not equals to yi. So it's basically the set of all indices where x and y differ. Yeah, and we saw how they prove this in the class. So I won't even give you a sketch of that proof. It was fairly simple. So then so far we have seen two main models of computation for Boolean functions, circuits, and formulas. Uh, this week we also saw a third model of computation called branching programs. So what are branching programs? Branching programs are directed acyclic graphs with one source vertex S and two sink vertices T0 and T1. And all non-sink vertices are labeled by a variable, and there are two outgoing edges corresponding to that variable being 0 and 1. The size of a branching program is equal to the number of nodes in it, and every S to TB path where B is in 0, comma 1 corresponds to a string in a natural way. So if a vertex is labeled by xi, then the edge labeled by bi going out of it corresponds to xi equals bi. And thus the label of all the edges on a path yield a string corresponding to that path. And a branching program computes if and only if for all x, f x equals b, if and only if there exists a path corresponding to x from S to TB. So when fx is 1, there should be a path from S to T1, and which corresponds to x, and when f of x is 0, then there should be a path from S to T0, which corresponds to x. So we also saw the notion of a layered branching program. So in a layered branching program, all the vertices are divided into layers, P0 to PD, such that every edge is between two vertices which are from adjacent layers. So every edge looks like u comma v, where u is in vi and v is in vi plus 1 for some I. And the width of a layered branching program is equal to the size of the largest layer. And then we saw Barrington's theorem, which proved that for any Boolean function f from 0, comma 1 to the end to 0, comma 1, it's an NC1 if but only if there it can be computed by a constant width poly n size branching program. In fact, the width is just 5. Okay, so this is what we saw in the class this week. So if there are no questions about this, we can look at the problems. Okay, so let's look at the problems. Just give me a second. Uh, okay, yeah. So let's look at the problems. So the first problem is uh, so let f be an so f is a Boolean function on two n variables, and I am thinking of these two n variables as this, like partitioned into two sets. I'll call these x and y. Okay, so we want to show that the communication complexity of any Boolean function on two n variables is at most n plus one. Now, a Boolean function is a relation, right? So a Boolean function over here is going to be a relation in and for x over here, y over here, you have 1 over here if fx comma y is 1, and 0 over here if x comma y is 0. Okay, yeah. So since a Boolean function is a relation, we can just use the previous definition of combination complexity that we had. And what this question asks us to do is to prove that for any Boolean function, the combination complexity is at the most n plus 1. Okay, so here's the setting. You have Alice, you have Bob. Alice has X in, Bob has Y in, and they want to compute f of x comma y, right? So one way would be for, okay, so okay, over here the function f is arbitrary. So we can't reason about f at all. We only have to reason from x and y, right? So one very simple strategy is for Alice to send x to Bob, Bob to send y to Alice, and then they can both have x comma y, they can compute f of x comma y, right? And this would give you a computation complexity of at most 2n. However, there is a much more simpler thing that you can do. So notice that, okay, so in the previous protocol that I suggested, at the when the after the protocol was executed, both Alice and Bob ended up with two strings x and y, and then from that they were able to compute f of x comma y, right? However, observe that let's say if only Alice knew both x comma y, then she can compute f of x comma y and send it to Bob, right? So the point is, both Alice and Bob need not know x and y. Just one of the parties knowing x and y is sufficient. Okay. And this naturally suggests the following protocol. So let's say Alice can send x to Bob. So now Bob is x and y. So Bob computes p equals to and sends b to Alice. And the number of bits communicated is so n for x and 1 for b, so n plus 1. Okay. In general, uh, okay, so instead of doing this for x comma y comma x cross y cross z, let me just say that all of them are bit strings, are sets of bit strings. Okay, so what's the smallest possible value of this? Okay, so we can do something similar. So let's say Alice has now, depending on which is smaller, M1 or M2, either Alice can send X to Bob or Bob can send Y to Alice, and then the person who gets both X and Y can compute one Z and send it to Bob, the other party, right? So, two cases. If Bob sends that such that, and if yeah, so the communication complexity, give me a second. Yeah, so the communication complexity is the minimum of M1, comma M2 plus M3. Now, here's one more protocol that, okay, here's one candidate protocol for this. Instead of, okay, so over here we sent X or Y depending on which of the M1 or M2 was smaller, right? To Y to save on the bits communicated, right? However, now suppose that M3 was greater than both M1 and M2, right? Then here's the protocol I'm proposing. Instead of sending Z, send Y, and then both Alice and Bob and have X and Y, then so they can compute the Z, right? So okay, the question is this protocol valid? Okay, well, it's not valid, and here's the reason. So, given X and Y, Alice and Bob might end up computing different Z, right? Okay, so okay, you don't encounter this problem if there is a unique Z for every X comma Y, right? However, Alice and Bob might end up computing different Zs, right? So, is there a way to overcome this issue? Well, there is. So, what Alice and Bob can do is, even before the protocol begins, they can agree upon sort of a table which is indexed by X, a table of the form X, table of the form X, Y, Z, where for every X and Y, they decide one Z. They decide to pick just one Z, right? One way to like realize this table would be like to say the following. Let's say for every X comma Y, you have multiple Zs. Pick the lexicographically smallest Z, right? So once they have this agreement, you can get a better protocol, and that better protocol would be this. Okay, so and um, and M3 is okay. Let me write this down like in a more different way. That would be more succinct. The first case is M3 is less than equals to both M1 and M2. Now, in this case, if M1 is less than M2, then Alice sends X, Bob sends Z. Z is such that X, comma Y, comma Z is in R. Uh, then if M2 is less than M1, then Y, Z, and again. And third case is like, let's say, uh, M3 is greater than M1 or M2. So let's say M3 is greater, in this case, X, Y, and both compute Z. Yeah, both of them can compute this individually. Right. Yeah. Okay, so in this case, the communication complexity was M1 plus M3, M2 plus M3, and here it was M1 plus M2. Okay, now in this case, M3 is smaller than both of these, and M2 is greater than M1, which means M3 and M1 are the smallest two, right, out of the three. Similarly, over here, M3 is smaller than M2 and M1, and M1 is greater than M2, which means M3 and M2 are the smallest two. And in this case, M3 is greater than all of both of these, so M1 and M2 are the smallest of the three, right? So communication complexity of R is okay. One way to write it is this, or like another way is to like pick the smallest, pick the second smallest, add the two of them. That's your communication complexity. So is this fine? Okay. Then let's look at the next problem. So the next problem is yes. So next problem is what are the communication complexities of or and oh wait it's not and let me write this properly or and and XOR as a functions. Yeah. So we want to find out the communication complexities of or to end and to end XOR to end. So as we saw in the previous question, all three of these are upper bounded by n over 1. The question is, can we do something better than n over 1? In fact, we'll see that we can do much better. And here it is just 2. And here's why. So again, you have Alice. Okay, so we want to compute x or y, right? Now, when is x or y 1? X or y is 1 if one of the bits of x is 1 or one of the bits of y is 1, right? So Alice did not send all the entire x to Bob. All it needs to send to Bob is the following. It needs to tell Bob whether any of its bits is 1 or if or not, right? So Alice can just send, let's say, B is defined as 0, let's say B is 0 if for all I xi is 0 and 1 if there exists I such that xi is 1. In other words, B is just the OR of all the bits of x. So it sends B to Bob. And what does Bob do? So if B is 1, then nothing. Because both of them know that since one bit of x is 1, or is going to be 1, so you are done. However, if B is 0, then Bob sends B prime. B prime is equal to, again, say, yeah. And at the end of the protocol, or is B if B is 1 and B prime if B is 0. And so the communication complexity is just 2. Yeah. So this fine. Okay. Phi is, yeah, okay. This is the case for AND is for AND the protocol is similar. So yeah, again, Alice need not say the entire X to Bob. So when is AND 0? AND is 0 if even one bit of X is 0 or even one bit of Y is 0, right? So again, Alice just needs to tell Bob whether all of its bits are 1 or not, right? So, oh, by the way, another way of writing this would have been B or B prime. Okay, so what Alice can do is, again, you can do something similar to what we did for OR. So Alice can send whether it is, whether Alice can basically tell Bob whether all of its bits are 0, if all of its bits are 1 or there exists a bit which is 0, and then Bob can reply with the same thing, right? So, okay, this time let me write it like this. So P equals and and so again the case for XOR is similar. Basically, we are using the fact that in all the three cases, we use the fact that end of X and Y is just the end of the bits of X and the bits of Y, and same for XOR. For yeah. And yeah, it's for all of these functions, the communication complexity is just 2. So is this fine? Okay, give me a minute. Okay. So the next problem is slightly longer. Spilled water on the iPad. Yeah. Or in other words, L is a subset of BP signs. Yeah. So in fact, we'll show something stronger. What we'll show is that there is a uh, there is a family of branching programs. There is a family of layered branching programs of polynomial size, which computes a language in every language in L. Okay, so let me connect my charger. Okay, it's charger. So branching programs compute functions, and so what we'll first do is we'll sort of break the language into a family of functions, right? So let okay, f n be this function. Yeah. So Fn is just basically, so the way to break a language into functions is that the family of functions is that you look at all the strings in of length n, and then you define the function Fn depending on whether the string is in the language or not, right? So we have defined Fn, and now what we'll do is we'll show that. There is a layered branch. Yeah, and then this would imply that L is in BP size entry order 1 because the family of Parche programs Pn would be the desired family. Right? So let's see how to prove this. So okay, and now we are going to design a branching program which basically emulates this Turing machine. So for this, let me define a few things. So okay, without loss of similarity, M has an input tape. So this tape is only read once as a work tape and an output tape. So it has just three tapes. And output tape is going to be write once. So essentially the only tape, yeah, so the only tape that counts towards the memory usage is the um, uh, work tape. Actually, since we are looking at languages, I think I can just get rid of the output tape because what it can do is at the end of its execution, it can just erase everything on its work tape and write 1 or 0 depending on whether it wants to accept or not. So at the end, it would just have 1 or 0 on its work tape, nothing else. Okay, and a work tape. And configuration. Yeah, so we are defining the configuration of A. sorry, configuration of M is as a tuple which contains the current state of M at any time, the position of the head of the input output tape, and all the contents of the work tape, right? And you don't need to store the, okay, let me do it. Yeah, so positions of the, let's say Q state and input and work and where uh, and yeah, so this is how we define the configuration. Now notice that let me call the configuration if you notice. So notice that the size of any configuration is order log n. Why? Because the state take constantly many bits because there are constantly many states. HI, the position of the head of the input output takes order log n bits because the size of the input is order n. The position of the head of the work tape takes order log n bits because there are only order log n many square cells of the work tape which are used. And W, the contents of the work tape. So since we only use logarithmically many cells, the size of W is also log n, right? The size of any configuration is at most log n. And let me say that, okay, the initial or start configuration. Uh, C1 be the, okay, CA be the accept configuration. Uh, okay, so now what we are going to do is, so now we want to create a branching program, right? Oh, I need to connect my charger. Okay, so now if we want to connect, construct a branching program. The branching program is going to be layered. Well, it's going to be almost layered. So here's how we're going to do it. So the source of the branching program, okay, so every node of the branching program would correspond to some configuration. The source of the branching program is going to correspond to C0. T1, the accepting sync is is going to correspond to CA, and the rejecting sync T0 is going to correspond to CR, right? So okay. Uh, yeah, so it's going to have T many layers, where T is the running time of M, and now we know that so now we know that space T for any T is contained in time 2 to the T for the same T, right? Now over here our space is log n, so it's contained in time 2 to the order log n, which is poly n, right? So the running time of the Turing machine is poly n, and it will have T many layers. Each layer, the zeroth layer, so yeah, contains just S. Yeah, so the first layer is just one node, the start configuration. The last layer is just the accept and the reject configuration. And every other layer contains every configuration except these three, right? So let uh, Yeah, it's fine. Yeah. Okay, so now I have told you what all the nodes in the graph are. I need to now tell you how the edges, what are these nodes labeled by and what the edges are, right? So the node labels are defined as follows. S is labeled by, okay, every node. Yeah, so every node is labeled by, okay, I'm using too many i's. Okay, let me call this J. So every node corresponds to a configuration. In every configuration, you would have HI, right? The head of the input output tape. Okay, let me call this HIP so that I don't confuse it with some other I. Yeah. So every node corresponds to a configuration, and every configuration has HIP, right? The which denotes the position of the input output head. So we label that node with HIP, X of HIP. So what are we doing? So when the head of the input output tape is on the cell HIP, what's in the cell HIP? So the cell 1 contains X1, 2 contains X2, and so on. So the cell HIP contains the variable X HIP, right? So basically what we are doing is we are labeling every node by by the variable which the configuration that the node corresponds to is reading, right? HIP. And okay, so let me do this for S first, and then I'll tell you for every HIG, right? So for S, start stages. So S is going to be labeled by X1 because at the beginning the input output head is on the first cell. And so the edge label 0 goes to V1C, where C is the configuration in which n ends up from C0 in one step if x1 equals to 0, right? So what this edge is doing is it's basically telling you that from the starting configuration, the machine would go to this configuration if x1 is 0. And similarly, there will be an edge labeled 1, which goes to a configuration C prime if C prime is the configuration that M ends up in if x1 were 1, right? So let me just copy it. Yeah, x1 is 1. Uh, for Okay, it's mostly the same. Let me copy it. P I plus 1 C prime. X H if C prime is equal to C accept or C reject, then the edge goes to T1 slash T0. Yeah, so as I said, uh, the answer problem is almost layered. So most edges go from layer I to layer I plus 1. That is the only exception is if the computation stops, right? So if you are done, then you would go from let's say you are in layer I, you are done. So you will directly go from that vertex to T0 or T1, the appropriate one, depending on whether it's accept or reject. So these are the sort of the only edges that jump from a layer I to directly the last layer. And similarly for one, yeah, the edge. And this is the same. Yeah, so this is a uh, construction of the branching program. So now let's look at the size. Okay, so notice that so this is how many layers does this have? This is T many layers, and each and every layer has at most like okay. So what's the number of configurations? The number of configurations is so the size of every configuration is order log n. So the number of configurations is 2 to the order log n, which is poly n, right? So our branching program has T many layers. In each and every layer, in the worst case, it has all the configurations. And there are some like for the last layer, it has one and two configurations. But yeah, just upper bound every the upper bound the size of every layer by all configurations, right? So there are T many layers, and in every layer there are at most poly configurations. So this is T times poly, but T itself was poly, so this entire thing is poly. And the width of the BP is also poly because every layer is at most poly configurations. So this is the construction of the branching program. Now let me quickly tell you, prove that this actually computes Fn, right? Uh, okay, so let X be yeah. So if Tn accepts X, then there must be a path S T1 comma C1, V2 comma C2, all the way up to Vt minus 1 comma Ct minus 1 comma T1 corresponding to X, right? Now, what we'll show is that sort of this path would, okay, so what do we want to show? We want to show that M of X is 1, right? Why? Because M accepts A and Fn is just A restricted to strings of length n, right? So what we'll do is we'll show that this path sort of corresponds to an accepting path for the Turing machine as well. So this is fairly easy to see. Yeah. So by the way we have constructed the Turing BP, Yeah, so because of the way we have constructed PN, this is true. Why? Because, okay, what was C1? C1 was the configuration that uh, M goes to from C0 if the input is X1, right? Similarly, C2 was what it goes to from C1 if the input was X1, X2, whatever was at the position where the head is, right? So, because of the way we have constructed Pn, M would end up on input X, M would end up in the configuration CA, right? That is, M accepts X, and so yeah. So if Pn accepts, then there is a part to T1. If Pn rejects, there is a part to T0, right? And again, yeah. So if Pn of X is 1, Fx is 1, and Pn of X is 0, Fx is 0, so Pn computes F. So we have a polysize branching program which computes Fn. And as we argued at the very beginning, this would prove that, yeah, there is a family of branching programs of polysize which compute A because the family is just Pn. Okay, so I hope this is fine. Okay, so then let's look at the next problem. Okay, so next problem is, so let me quickly tell you what L slash poly is. So L slash poly is the class for languages that are accepted by log space Turing machines with advice. Okay, that take advice. Now, they take advice of poly many bits. So, what is an advice? So, an advice is the following. For every input length n, it's a string an, which is given to the Turing machine along with the input, right? Yeah, and we want to show that BP size n to the O1 is contained in L poly. Yeah, so This is sort of the converse of the previous question. So in the previous question, we showed that L is in B, PP lies n to the O1. In fact, that proof can actually be extended to show that L slash poly is in BP size n to the order 1. But yeah, I mean, it's a very simple extension. You just have to, yeah, on now your input tape would also have a device, and that device is still of poly and length. So over here, so your earlier your input output head should only had to go till xn. Now it has after x it has a device, so it has to read the device as well. But x combined with the device is still poly and bits. So the input output, so the position of the input output head can still be expressed using order log in bits, and so the rest of the proof would work straight up. Yeah. So basically, what 3 and 4 together would show is that EP size n to the order 1 is the same as L slash 4. Okay. So PN is linear. Okay. So now what we want to do is we want to consider a log space Turing machine from this PN, right? So okay. So we have such we want to consider okay we have constructed a Turing machine which does we want to consider a Turing machine which does the following. It is given PN as a device, and it uses this PN to output 1 or 0 depending on whether there is a path from S to T1 in PN. That is, it outputs 1 if and only if PN outputs 1, right? So clearly, M, okay, let me, yeah, so M decides the language. This much is clear. all I need to do now is to show that M is a log space machine, right? Now, notice that Tn is a graph of poly size. So I can easily find if there is a path from S to T, T1 corresponding to X in poly time, right? So this would immediately show that BP size n to the order 1 is in P slash poly. But I want to do something stronger. I want to show that it's an L slash poly. So I need to show that the Turing machine M can find such a path from S to T1 if one exists in in a log space, right? And here's where we are going to use the fact that the branching program is layered. So what we do is the following. Okay, okay. So M is supposed to trace a path, right? Okay, so yeah, so suppose that at some point in time it is at this node, right? Okay, yeah. So suppose that at some point it is at Vi. Okay, now okay, so the branching program is layered. So we know that the next uh, so any neighbor of Vi, so any node, so the next node on the path is going to be the layer I plus one, right? Yeah, so all all M has to do is this. How can it find this? It can, right, and observe that. Yeah, so right now it's at vi. It wants to go to one of its neighbors appropriately, whether depending on whether the variable that labels vi is 0 or 1 in the string. And to do this, all it has to do is to look at the branching program pm and find out which node this is in layer I plus 1, right? Now to look to search for the appropriate node in the branching program, all it needs to know is what vi is. So all it needs to store on its work tape is vi. So in this process of tracing the path, the ith step, the only thing it needs on its work tape is vi. Okay, and once it has found vi plus 1, it can replace vi with vi plus 1. So I so the space used is order log. Why? Because Pn is a poly-sized uh, transit program, and therefore it only needs you only need order log n many bits to index any of the node, right? And observe that. Uh, yeah. So at the first step, it goes from 0 to the first level layer. The second step from first to the second level, and so on. So that was t layers in t steps. It would halt, and it would halt having found a path in T0 to T1, and so it can output 1 or 0 appropriately, right? So here we have shown a way to implement this to find this path from S to T0 or T1 in time, sorry, using just order log n space. And so, yeah, M is a log space machine, and we are done. Is this fine? Okay, so if this is fine, in this question, we made an assumption that every language in BP size polyN has a polyN size layered ABP, right? From a definition, the only thing that follows is that it has a polyN sized AB, it has a polyN sized branching program, right? So now we need to show, to complete the proof, we need to show that uh, if if uh, if there is a branching program of size S, there is an equivalent branching program, equivalent layered branching program of size poly S, right? And that's the next problem. Okay, so in a layered branching program, the vertices are divided into so the vertex set is partitioned into layers, right? So first, I need to define what the layers are. Okay, so for all I in S, Vi, okay, let yeah. So this is just the set of all nodes. So that the longest path is length I, and there are at most as many layers because there are at most as many nodes in the in the BP, and so any path can have length at most s, right? So now, okay, so I've divided the vertex set like this, but now there might be edges going from let's say Vi to Vj when I and J are not the same, right? So we need to handle this as well. Okay, so for this, okay, so let me do it like this. Union two new nodes. U Yeah, so this is our yeah, and V0 is just S. Okay, so this is our these are our vertex sets. Okay, now I need to show you how to ensure that every edge goes from one layer to the immediately the next layer, right? So first of all, notice that in P, so my claim is that in P, every edge goes from a vertex in the smaller layer to vertex in the larger layer. Let's see why. So suppose that this were not true. Suppose that there were a vertex in layer, let's say V10 and a vertex in layer V20. Let's say the vertices are U and V. So that there was an edge from V to U. Okay. Okay. So now V is in V2. Is in the 20th layer. What does that mean? That means that the length of the longest path to V is 20. And since um, there is an edge from V to U, the length of the longest path from S to U is at least 21, right? But then uh, U has to be in layer 21 or larger, right? It cannot be layer 10. So because of the very way we have defined Vi, in P, every edge goes from a vertex in a smaller layer to vertex in a larger layer. Okay. So so after I've defined the vertex edge like this, P is almost layered. The only issue is that, yeah, I mean, you might have edges going from V10 to V20, but in a in a layered branching program, the edges are supposed to go from V10 to V11, V12, and so on up to V20, right? So I just need to fix this. Also, V0 to VS are disjoint sets. Oh, so this symbol means disjoint union. So you have disjoint sets. And they are disjoint sets because uh, if any vertex is in layer Vi, then the longest path from S to that vertex has length I. So it cannot be some other layer J because that would mean that the longest path has length J. There is only one longest path, right? Yeah. So its vertex that is this. Okay, so this is the vertex set. Now I have to show you how they are labeled, right? So for I for every vertex other than the vertices of the form UI0, UI1. Yeah, so it has the same label as in P. And now I need to show you how I'm labeling UI0, UI1. So I'm labeling them by X1. It doesn't matter if you label them by any variable, it would be fine. So there might be some edges in P which go from one layer to the adjacent layer, right? So all of these we add in P prime, these are completely fine. For all the other edges, Oh, wait. Yeah, so this is how we have constructed P prime. So now let's first quickly look at the size of it. So size is now we need to show that this computes the same function as P, right? So okay, we don't have too much time, and we also need to cover the assignments from uh, like this year, this week 9 assignment. So let me okay quickly. So let me not write it down. Let me just quickly tell you why this is true. Okay. So suppose that P accepts a string X, then there is a path from uh, uh, S to T1 in P, right? Now this path, okay, so I, I want to show that a corresponding path exists in P prime, right? So suppose look at any edge in this path, U to V. The only issue might be when U and V are in layers that are far apart, right? So let's say U is in V10 and V is in V20. Okay. But in that case, what have we done in P prime? In P prime, there would be a so let's say this is U and this is V. This is a layer 10, this is a layer 20. Then in P prime, there would either be a path from U to U11, comma 0, U11, comma, sorry, 12, comma 0, U13, comma 0, and so on, right? When when would this be the case? If the edge labeled from U to yeah, so if the edge U to V has labeled um, 0, right? Similarly, if it has label 1, there would be a path from U11, U11, comma 1, U11, comma 12, comma 1, and so on, right? So, if there is a path in P, there would be a longer path in P prime, right? Similarly, if there is a path in P prime, how is it? Okay, so the, the only issue is like, okay, these path might contain edges of the from edges that go from some vertex to a vertex UI0, UI1, right? But for every such uh, path, you can sort of short circuit it by just looking at the last non U1 UI1 UI0 vertex and the first non UI plus J. Yeah, so if there is a path in P, right, there is always a path in P. Okay, so I won't prove it. Yeah, so it's this. Okay. Uh, Now, let's look at this year's peak nine assignment. So the first question is, pick the smallest number of clauses in any CNF formula for parity. The options are 2 to the n, 2 to the n minus 1, 2 to the n minus 1, and 2 to the n minus 2. So which of these is correct? The correct option is 2 to the n minus 1. Why? Because the parity has, yeah. So the next problem is, let C be a non-empty clause in uh, DNA. With W literal, so that no variable x, for no variable x, both x and not x are present in C. What is the fewest number of variables which must be fixed so that C becomes? So it's a clause of DNF. So it looks like wait, wait, no, 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 it's a clause of a CNF here. Yeah, so it's a clause of a CNF. So it looks like an or of a bunch of things, right? And since it's an or of a bunch of things, you need to only fix one variable to make it one, but you need to fix all variables to make it zero, right? So the option C is correct. Now pick the highest lower bound on depth d greater than 2 unbounded Fallon circuit for parity on n variables. The options are 2 to the omega n square over d, 2 to the omega n to the 1 over d, 2 to the omega n to the 1 over d square, and 2 to the omega 1 over log d. So this is just like this is the lower bound proof that we saw for parity, right? In class last week, and the answer was 2 to the omega n to the 1 over d. This is what you can prove of Hartsat switching law as we saw in class. So the next problem is, what is the maximum bit of a clause in an optimal CNF for parity? The options are n minus 1, order n, log n, order n over 2. And the answer is order n because uh, and as we saw in class, if a function has uh, maximums of size n, then any CNF computing it must have clauses with width. Okay. We can suppose f can be written as an n to the order of a CNF, and we apply a random restriction with p equals n to the minus 4.5. Then what is the smallest upper bound on the probability that f rho cannot be written as an order log n DNF? So start switching your bus as that. Uh, So over here, C is the constant. P is yeah. So this is n to the minus 1.4 log n. So let Rk be the set of all restrictions that leave key variables unfixed. What's the size of Rk? So yeah. So k variables are fixed. So k variables are unfixed. Sorry, k variables are unfixed. So uh, n minus k variables are fixed. So the number of way of choosing n minus k variables to fix is n choose n minus k. And each variable can take two values. So the number of values they can take is 2 to the n minus k. And this is just n choose k times. Yeah, because n choose n minus k and n choose k are the same. So it's k. So in Rasbarov's proof of the switching lemma, AI is a sequence of t-bit strings where AI denotes which variable of the class Ci are fixed. Pick the best upper bound on the number of such sequences. So first, K is at most S minus 1. And so each pi I, yeah, and now what we'll do is to count the number of AIs, write separators, and then to be a string with bunch of zeros and ones. And you can characterize this string by, so sort of think of the ones as partitions. So think of ones as following partitions of the string, and you can characterize, there will be at most s partitions because there are s minus 1, at most s minus 1 ones. And so you can characterize every string by how many zeros are there between any two ones, right? So how many zeros are there in any two partitions? So And since every AI has at least one partition, and the size of every AI is T, uh, length of every partition equals to 2 times T. And so you have at most as many partitions in between any in any partition. Like you have, oh wait, yeah, this will be 2s minus 2 because yeah, two of those will be occupied by ones. Yeah. So you have at most s partitions, and I need to tell you how many zeros are there in between these partitions, right? So the number of zeros is anywhere. So how many choices do I have for that? From 0 to 2 to the t by to 2 t minus 2, right? So I have 2 t minus 1 choices. So this is at most so it's C. And finally, let f be the OR function of n variables. Let rho be a random restriction. Pick the best upper bound of the probability that f rho cannot be written as a 3D. Well, this is 0 because uh, f rho is still an OR. Yeah, so f rho, let's say the variables that remain are xi1 to xim. F rho is just an OR of these, and every OR can be written by one DNF, right? Because this expression over here is a one DNF. Every clause has size 1. Yeah, so every uh, f rho can be triple written as a one DNF, so it can be written as a 3 DNF. It's probability 1, so the probability that it cannot be written as a 3 DNF is 0. Yeah, so is this fine? So that's it for today. Let's meet next time. Bye.